Hello, my name is Isaac Burnett, and today I'll be presenting on hyperbolas and their uses. So what is a hyperbola and where are they used? Hyperbolas are a curve or pair of curves that are made up of points that maintain an equal difference of distances from two points called foci, such that any point lying on those curves, if you measure their distance to each of the foci and take the difference of these two measurements, which means you will always receive the same number. They are made by taking a planar intersection of an infinite cone such that that plane intersects both sections of the cone with a gap in between them. And when are they used? They are used in the design of some cooling towers for the water vapor and other byproducts of nuclear and coal power plants. These are designed as hyperboloids created by rotating a hyperbola around its vertical axis. They also describe gravitational escape vectors in our world, such that if an object passes by a gravitational center, such as a planet or a star, the path that it traces will be described by a hyperbola with a focus placed at that gravitational source. Although in this case, you only see one part of the hyperbola. So how can we describe hyperbolas? They're presented with the general form of x minus h squared divided by a squared, and subtracting y minus k squared divided by b squared, and setting this all equal to 1. A third value c is derived from the Pythagorean relationship of c squared equaling a squared plus b squared. Hyperbola will be centered at the point hk in terms of the original formula, with foci placed at h plus or minus ck and vertexes being placed at h plus or minus ak. If you want a hyperbola that opens upwards and downwards, this would be a hyperbola with y is the positive term and x is the negative term, and the foci would be described in terms of k and b, such that h plus or minus k plus or minus c is where the foci are on a vertical hyperbola, and hk plus or minus b describing its vertexes. Another useful measurement for hyperbolas are the asymptotes, which will be at plus or minus b times x minus h divided by a plus k. And this will be similarly inverted for a vertically aligned hyperbola, such that a times y minus k divided by b plus h in that case. So how can we use this in design? Cooling towers need to be very wide at the base to give them a strong foundation, but they need to narrow towards the middle so that they can accelerate the air and make it move faster and become more turbulent. And then they need to expand once more to cause rapid condensation so that much of the water can be recovered. This is because most of the water is heavily treated, and so it's not very cheap water, and they like to get most of it back. So, say the engineers determined they need to have a tower that is 170 meters tall, narrows at 175 meters, and the width measurements range at 150 meters at the base, narrowing down to 80 meters at 105 meters upwards, and expanding back out to 84 meters at the 170 meter peak. This is all that you need in order to determine what the formula of this hyperbola should be. First, we can identify the vertices. The vertices will be at this narrowest choke point, and we will assume h to be 0, such that the graph is centered at the center of this tower. In this case, if it needs to be 80 meters wide, you need to take plus or minus 40 at 145 meters up. So you can set 2 points on this graph to be plus or minus 40, 145. This will give you the vertices of your graph. Y. A is a measurement of the sort of horizontal width, such that the difference between the two vertices half of that is A, which so in this case is simply 40. D. And since the vertex is 145 meters of the ground, K is equal to 145, giving us our new equation, almost complete, at x squared divided by 40 squared minus y minus 145 squared divided by b equals 1. B squared equals 1. Now we just need to learn what b is so we can complete our formula. So we will plug in any point on the graph. I chose one towards the bottom at 75, 0. Remember, it's 150 meters wide, so it's only 75 meters out towards the right. That's right. And this gives us 75 squared divided by 40 squared minus 0 minus 145 squared divided by b squared equaling 1. And now we simply need to solve this equation for b. So first we will move our y term to the right and bring our 1 over to the left to give us a new equation of 75 squared divided by 40 squared minus 1 equals 145 squared divided by b squared. We're going to bring that 1 inside of the x terms by setting it equal to negative 40 squared over 40 squared. So we can have our new equation of 75 squared minus 40 squared all divided by 40 squared equal to 145 squared divided by b squared. Now we multiply both sides by b squared and divide both sides by our left term, which is a mouthful, to get b squared equals 145 squared times 40 squared divided by 75 squared minus 40 squared. This gets pretty big and messy, but after a little bit of simplification and reducing our denominators by 25, we get that b squared is equal to 1,345,600 divided by 161, which is a monstrous term. And we could square root this to get a more exact value, but we don't need to know b in this case, although it is around 90. So our final formula to describe this hyperbola is x squared divided by 1600 minus 161 times y minus 145 squared divided by 1,345,600, all equal to 1, which is a mouthful. This also means that our foci are placed quite far out, I believe, at plus or minus 60, if I remember correctly, which means their foci are actually further out than the top of our tower. You can see on the graph I put bounding lines for the height of our tower, and you can see it passes cleanly through our vertices and our known points. The last thing you would need to do in this graph is to rotate these points around that vertical axis, and you will trace out an iconic shape of a cooling tower. Quite frankly, we just made a cross-section of a rotationally symmetric object. You could also rotate these around the x-axis, but that would give you two bowl shapes, which are much less useful. I'd like to thank the hyperbola image source from the clip arts that I was able to find, and I made the hyperbola graph using Desmos. And thank you, Professor Meg Bartran and Professor Ryan Orr, for teaching me about hyperbolas.